Hello, my name is Daniel Grimmer. I am a master's student doing my MST in philosophy of physics. This was a presentation that I gave at the Philosophy of Physics graduate lunch at Oxford. That's the PopGrunch is the name of it when shortened. Unfortunately, that talk was not recorded, but these are exactly the slides that I gave, and I'll try and remember the questions that people asked. I'd just like to have a video record or a video companion to go along with these slides. And the slides are available at my personal website, users.ox.ac.uk/tilde Pemb, that's my college, 6003. That's the website, and the specific page is talks, if you go there. So I'm currently a master's student, as I mentioned, but I've applied to do a DPhil here at Oxford, and this is sort of the research proposal associated with my DPhil application. So I'll be talking about a discrete analog of general covariance, and I think there's a lot of interesting material and a lot of interesting philosophical discussion that can come out of this sort of thing, enough to fill up a PhD, I'm hoping. So with that said, let's just jump right into it. So this talk will be divided into 3 parts. Part 1, I'll review what is special about general relativity. In this, I'll follow Pooley in a 2013 or 2015, I can't remember, paper, which goes into these in tremendous detail and great clarity as well, I should say. So we'll give this part of the presentation, and the goal here is to differentiate the concepts of general covariance, diffeomorphism invariance, and background independence. These 3 concepts are distinct and should be thought of as distinct, and I'm not going to settle any questions here about what background independence is or how it ought to be formulated. There's a lot of uncertainty about that. The main purpose of this first section is to differentiate these 3, and in particular, show how general covariance plays a supporting role to diffeomorphism invariance and background independence. But more on that later. This is sections I'll review. In the second section, I'll review the Nyquist-Shannon sampling theory. This is the main mathematical tool used in the third part. We'll have to talk about band-limited functions and uniform sampling and non-uniform sampling. This will all make sense once we're done with this part. And then in the third part, I will put the first 2 parts together, producing the novel content of this talk. And we'll see what exactly this discrete general covariance I'm going to talk about is. So put the 2 together there. Okay. I will break this into 3 different parts. There'll be 3 sections to the video and maybe a 4th one where I talk about the outlook. In the talk, I would pause for presentation for questions at each part, but we'll just skip through it. I'll try and remember what the major questions asked during the PopGrunch talk were and address them at the end. So, part 1, some philosophy of GR. So what's special about GR and GR-like theories as opposed to merely special relativity-like theories? Again, there's this Pooley paper from 2013, background independence, diffeomorphism invariance, and the meaning of coordinates, which lays this all out very clearly. And I would suggest going to there if you have any further questions about this portion of the talk. So could it potentially be general relativity's general covariance, which makes it special? This was indeed the first theory in history to have this property of general covariance, which is the fact that its laws take the same form in all coordinate systems. So it's possible that this is the great leap forward, if you want to think of it that way, that Einstein made when he moved from special relativity to general relativity. It could also be GR's diffeomorphism invariance. Again, this was the first theory in history to have this property, and so it's a contender for what might be special about general relativity. And this is, technically speaking, the fact that the symmetry group of general relativity is the diffeomorphism group over the manifold. This is in some sense the largest symmetry group, largest space-time symmetry group that's possible for a manifold. So it's sort of maximally symmetric in a way. Or C, could it be GR's background independence? And again, there's a lot of divergent ideas about what exactly background independence is, but roughly it's the fact that GR has no fixed background structure, although what exactly that means deserves a lot more attention. So in the first part of this talk, I'll talk about how these 3 concepts differ from each other and how they're related to each other. But again, the goal is to talk about how general covariance plays a supporting role for these other two. Because to give an overview of the main idea, I'm going to take general covariance and introduce it then to a discrete setting, a lattice theories, right? And from this discrete extension of this concept, we'll then potentially be able to obtain extensions of diffeomorphism invariants and symmetries in general and background independence into these discrete contexts. So this is the first attempt to break through, and then the extension to these will likely follow from that. Okay, here's the spoiler for part one. Here's the answer to the question, what's special about GR? Was it A, general covariance? No, general covariance is not a special property of general relativity. It turns out that any theory can be made generally covariant. And this was pointed out by Kretschmann early on in the history of general relativity in 1917. And a good review of the history of this subject is given by Norton here in this 1993 paper. But nonetheless, general covariance is important because it exposes background structure and clarifies many questions about symmetries. This is what I've been repeating throughout the last few minutes, that general covariance plays a supporting role to the other two. I'd really like to stress that here. Okay, could it be diffeomorphism invariance? No, diffeomorphism invariance is not a special property of general relativity. And this may be surprising for some physicists. Certainly when I've given this presentation to physicists, they're a bit surprised by this fact. But it turns out, as I will show, and as Pooley again talks about in much more detail and clarity, special relativity can be rewritten in a diffeomorphism invariant form. But nonetheless, diffeomorphism invariance is important because it is a necessary condition for background independence. Roughly, anything which breaks the diffeomorphism symmetry will count as background structure. And again, that's very rough. I'm not going to say exactly what background structure is here. But background independence, this vague concept which I refuse to define, is what makes GR special. This is generally the consensus as I understand it, but there's a lot of details about what exactly goes into that definition. So let's go into a concrete example of general covariance and continuous here, because I'll be introducing a discrete version later. Example one here is the Klein-Gordon equation. So consider phi to be a real field here. Second derivative in time is equal to the second derivatives in space along with a mass term acting on the function here, the field. Now, at any point in the talk, you can take m to be equal to 0. The mass, the fact that it's non-zero is irrelevant. I've just added it in to sort of show how the theory works. This formulation of the Klein-Gordon equation is not generally covariant. And how we can see that is if we write it in terms of new coordinates, t prime, x prime, y prime, and z prime, where x prime is just a shifted version of x, a dynamically shifted version, which is in some sense accelerating in a Galilean way. Then what we have afterwards is here are the coordinates for the new field. So here's the differential equation that the field obeys in the new coordinates. So time derivatives equaling space derivatives in a mass term, but there's a new term that shows up, which is related to fictitious forces or to non-inertial frames. So in arbitrary coordinates, we find extra terms due to the non-inertial frame that we're describing things in. That's what I just said here. And let's do that now in general. So from Cartesian coordinates, x mu, here, we can write our Klein-Gordon equation in this way. We've introduced this eta Lorentzian metric, which has a signature of -1, 1, 1, 1. If we transition from here to arbitrary coordinates x prime, you can just grind it out, and you see that this new field obeys this equation here, 4. So the metric has been modified by these two change of basis matrices, and we also have these second derivative terms which show up in our equation here, related to fictitious forces or Christoffel symbols, however you like to think of it. So this is not the generally covariant formulation of the Klein-Gordon equation, but we can arrive at one by moving away from coordinates altogether. We could write our theory in the coordinate-independent language of differential geometry. To see how this works, consider the space of kinematically possible models, which are here given by a manifold M, a metric, a Lorentzian metric AB, and a field phi. So manifold 3 plus 1. Eta here is a fixed metric field with signature same as before. and phi is a map from the manifold to the reals, is a real scalar field. Now, then these are the kinematically possible models, which state sort of the mathematical scenery around our theory. Just given these objects, it's probably not a dynamically valid solution. Those are picked out by the dynamically possible models, which is a subset of the kinematically possible models. And in this case, these are picked out by this contraction of the metric with these derivative operators at minus n squared acting on the field giving 0. This is the dynamical equation. And in particular, this is the unique derivative, which is compatible with the metric, that is, which has the derivative of the metric being 0. And now to clarify something at this point, when I write objects like eta AB and these covariant derivative operators, I don't mean the representation in a particular coordinate system. I'm thinking of eta and nabla here as the abstract geometrical objects themselves. These indices are just to indicate how many times covariant this is and how many times contravariant this is. Or strike that, reverse it. I think I said that wrong. Anyway, it just says what the rank of the tensors are and how they contract with each other. I'm not really thinking of it as coordinates, as its representation in a coordinate basis. So with that clarified, let's move on. So here we have the Klein-Gordon equation in a generally covariant form. Manifold Lorentzian metric field with eta AB fixed. This is important. And the dPMs here. So the fact that eta AB is fixed across all solution qualifies it as background structure. Now, I mentioned earlier that there's not uniform agreement about what background structure is, but it's uniformly agreed that this is the case, that this is one. Right? And this fact this fixed field exists break diffeomorphism invariants of the manifold M. Note, I've called this SR1 in line with Pooley's notation in the paper that I'm following along with here. Given a generic diffeomorphism D and some solution, doing the pushback or the pull forward, whichever is relevant, on the geometrical objects here, we find that transforming both objects is not a solution in general, and transforming just the field is also not a solution in general. These are only going to be solutions in the special case where D is in the Poincare group. So this is how the metric breaks the diffeomorphism invariance of the manifold and makes, and like I mentioned earlier, anything which breaks the symmetries of the manifold will end up counting as background structure. So that is how we do general covariance for the Klein-Gordon equation. What we can do next is repeat the process for the heat equation. Again, you can write any equations you like in a generally covariant way. I'm going to show you how to do that now for this equation. The time derivative of some heat field is proportional to the second space derivatives of the field. So working this out, we find the continuum heat equation has KPMs of this variety. We have a manifold, we have a space metric, a time metric, a covariant derivative, a time-like field here, A, and the heat field, psi. There's a lot of details to this, which are not really relevant. You don't need to remember or use the details of this for the rest of the talk, but let me just go through it quickly once. This consists of a fixed space and time metric, HAB and TAB here, with signatures 0, 1, 1, and 1, 0, 0, respectively. So these metrics are singular, and that's important for the dynamics later. And these two are fixed beforehand, I've mentioned, and they are fixed such that they are orthogonal to each other. The contraction of HAB and TBC is 0. We also have a fixed covariant derivative operator, nabla A, and it's compatible with these metrics. The derivative is here 0, and the derivative of the time metric is also 0. Now, in a Lorentzian manifold, compatibility with the metric picks out a unique derivative, but here it does not, because these things are singular. So we have some extra freedom left in our derivative operator. We'd like to fix it. So we also demand that it's flat here. So the Riemann tensor here, which is constructed out of this, is going to be 0. And lastly, we have a fixed vector field TA here, and this sort of points the way forward in time. It's a constant vector field, meaning that its derivative is 0. It's time-like, so that its contraction with the time metric is positive. It's future oriented also. I mean, it's so it's pointed into the future, and it's normalized here such that TAB contracted with these is 1. So it has a unit time-like future-oriented normal vector field, which is constant. That's a mouthful, but that's the structure assumed by this. And the role that TA plays in this theory is that it picks out a canonical way of moving forward in time. That is, translations by the contraction of TA with the covariant derivative here. So in total, from this, we have the heat equation here, reformulated with all of these background objects. The only thing which isn't fixed is the dynamical field psi. And then it has its dynamics fixed at the level of the dPMs, which in this case are picked out by here, the contraction of vector here. So this is the derivative in the TA direction is equal to the derivative in, well, the HBC direction, sort of. It's the second derivative here. Right. So that was the heat equation. One more example here is the example of Newtonian gravity. So repeating this process for Newtonian gravity, we have the same sort of thing. A time metric, a space metric, a covariant derivative, a gravitational field, a gravitational potential, sorry, and capital phi here is just a stand-in for the matter content generally. And these geometrical objects are fixed as background structure beforehand. And the dPMs here are given by Poisson equation, and then something here which says that the geodesic deviation of some particle is given by this force here, which is the gravitational force. So I mentioned what all of these are. Rho here, the energy density, is calculated from capital phi somehow. In a similar way how the stress energy tensor in general relativity is constructed from the other fields present in the theory. And UA here is the forward velocity of some test particle, which is normalized in time-like. Right, so here we have Newtonian gravity. And an important note here is that there's no time-like vector field TA here, so that this theory then has a Galilean symmetry group, whereas the prior one didn't. It had like a Euclidean symmetry group plus a time translation. All right, so enough of giving theories in generally covariant forms. And those three theories I mentioned earlier will show up again later in the talk. So that's why I spent the time to introduce them. But what are the benefits of writing something in a generally covariant way? Writing a theory in a coordinate independent way, the effect of this is to separate the theory's substantive content from its superficial coordinate dependent properties. We think of coordinates as just a representational system, and so the particulars of the coordinates shouldn't matter at all, and anything that's related to them is unreal. We can definitely say that. So when we write things in a coordinate independent way, everything that's left sort of is something which we could potentially consider real in our theory. And in this sense, it exposes background structure. And moreover, it clarifies questions about symmetry. Since any theory can be written in terms of any coordinates, or in terms of no coordinates at all, in fact, it should be now obvious that coordinates play no role in symmetry. In particular, the coordinate independent framing, there are no such things as passive symmetry transformations. Those are either trivial or they don't exist, depending on how you look at it, I think. So this clarifies questions that we have about symmetry. So what about diffeomorphism invariance? Could that be what makes GR-like theories different from SR-like theories? We're still following Pooley here. I give another reference to him. So unfortunately, this is not right. And this is very confusing for a lot of people that I've spoken to, especially physicists. But this example is laid out by Pooley quite clearly. And if you have questions about it, I highly recommend reading this paper. We can reformulate special relativity to be diffeomorphism invariant in this way, called SR2 following Pooley. These KPMs are the manifold, a Lorentzian metric, which is now dynamical, not fixed, and a field phi here. So this is the same sort of KPMs that general relativity has, but I'll say a little bit more about that later. And the dynamically possible models here are picked out by now two equations, one which is the Klein-Gordon equation in this potentially curved spacetime, and another which guarantees that actually the spacetime is not curved. So a flatness is composed on the metric sort of dynamically. Now this may seem a little bit like cheating, but it is a valid way to write down special relativity, or this reformulation of special relativity, if you want to think of them as different things. What it means is, well, let me talk about the symmetries for 1 second. Given a generic diffeomorphism and a solution to 12, we do in fact have the transformed version with all the geometric objects pulled through, pulled around by the diffeomorphism. This is also a solution. So in that sense, this theory does have a diffeomorphism symmetry, even though its solutions are one-to-one, not one-to-one, but each of these solutions maps onto one solution of special relativity 1. There's an extra sort of gaugey type freedom induced here. In any case, what this means is that if we pick up a theory in the wild and we notice that it has this diffeomorphism symmetry, right? We notice that we take a solution, transform everything, and get a new solution. This doesn't mean that the theory is GR-like, because it could be, in fact, this thing which is very special relativity-like, if it's not exactly special relativity. So diffeomorphism invariance can't be exactly what you mean when you say background independence, or when you say what makes general relativity different from special relativity. So here, I've written down special relativity 2 and general relativity side by side. In this case, at the level of KPMs, these theories are identical. So they talk about the same types of objects exactly here. And it's just that the dynamical equation of how the curvature relates to the matter is changed here. Here, it's fixed to be flat, independent of what the matter is doing. And here, it's curved based on what the matter is doing. So intuitively, special relativity 2 has something like background structure, whereas general relativity doesn't, but it's a bit difficult to spell that out and say exactly how that works. Which is just what I say here. But what exactly is the background structure in SR2? It's again unclear, and my talk is not about this, but I just wanted to bring it up. So what exactly is that background structure, and how can we confidently identify background structure in other theories? That's a big question, lots of debate about it. So there is much ongoing discussion in the philosophy literature about how exactly background independence should be formulated. There's too much to get into here. If you look up this topic, you'll find plenty of references on it. For the rest of the talk, all that's important is that we understand how general covariance supports our understanding of diffeomorphism invariance and background structure. In particular, here's the take-home message from the first part. General covariance is important because it exposes background structure and clarifies questions about symmetries. Now, when we carry general covariance into the discrete context, it will have the same effect. It will expose background structure, whatever there may be, and it will clarify questions about symmetry for us. So before I move on to part 2, any questions? Feel free to post them in the comments below.